This is talking about integer exponents and scientific notation. X to a power n. X is called the base, n is called the exponent or power. It is equal to, well, you start with a 1, you multiply by x n times. So x to the first power is just x. X to the second power is x times x, called x squared, because if you have a square with side x, then the area is x times x, therefore the name x squared. X to the third power is x times x times x, called x cubed, for a similar reason. If you have a cube with side x, then the volume is x times x times x, x to the third power. X to the fourth is 4x is multiplied, x times x times x times x. I suppose if we wanted to continue with a geometric analogy, we should call it x tesseracted or something. But tesseracts are for cultists and science fiction writers, so never mind. Now, if you have different powers of x, you multiply them, you add the powers. So for example, x to the second times x to the third, that's 2x's times 3x's, that's 5x's, and you get the 5 from a 2 plus 3. In general, x to the a times x to the b is x to the power a plus b. You multiply powers of x's by adding the powers. Here's something slightly different, a repeated exponent, not a cube times a square. This is a cube of a square. X squared cubed. Well, that's x squared times x squared times x squared. Since we're multiplying these, we add the exponents, x to the 2 plus 2 plus 2. That's x to the 6th power. And get a 6 from a 2 and a 3 by multiplying x to the power 2 plus 3. In general, if you have a repeated exponent, an exponent of an exponent, you multiply the exponents. X to the a to the power b is x to the power ab. Here we have a power of a product, xy squared. Well, that's xy times xy. But then you rearrange these to put the x's next to each other and the y's next to each other. This is x to the second. This is y to the second. So xy to the second is x to the second times y to the second. In general, xy, that to a power a, is x to the a times y to the a. So this power distributes over multiplication, pretty much the same way that multiplication distributes over addition. And indeed, when we later on get to logarithms, we see that the analogy is exact. Here we have a power of a quotient of a ratio, x over y to the second. Well, that's x over y times x over y. That's xx over y, which is x to the second over y to the second. So the second power distributes over the ratio. And that does in general. X over y to the power a is x to the a over y to the a. So powers distribute over divisions, sort of like the same way how multiplication distributes over subtraction. Now, if you have power, that's the previous power times x. So x to the n over x is x to the n plus 1. We can use this rule to help us define x to 0 and negative powers. X to the 0, well, that should be x to the 1 minus 1. That's what a 0 is. It'll be x to the first divided by x, which is x over x, which is 1. X to the 0 should be 1. That makes sense if we go all the way back here. X to the 0, we start with a 1, then we multiply by no x's, which equals x to the 1 equals x to the 0 equals 1. Now, how about negative powers? Well, x to the negative 1 is x to the 0 minus 1. That'll be x to the 0 over x by this rule. And that'll be 1 over x. X to the negative 2, that's x to the negative 1 over 1. That's x to the negative 1 over x. It's 1 over x divided by x again, which is 1 over x squared. And so on. In general, to a 0, x to a 0th power will be 1. And x to a negative n power equals 1 over x to the n. So a negative power means the reciprocal of a positive power. This also means that reciprocal of a negative power is a positive power. They're reciprocals of each other. And you have a ratio of negative powers. You basically have to switch them up, numerator and denominator. X to the negative m over y to the negative n is y to the n over x to the m. So for example, x to 2 over x to the 5. Well, it's 2x's over 5x's, 2 cancels, leaving 1 over x to the third. x to the negative third, 2 minus 5. X to the second over x to the second is 1. That's x to the 0, which makes sense. X to the 5 over x to the second. You subtract 5 minus 2 and you get x to the third. So in general, if you have a ratio of powers, you subtract the powers. X to the a over x to the b is x to the power a minus b. And we use this negative power definition to make it make sense. So for example, we'll get back to scientific notation in a few moments. So here we go. X to the third times 5 is what? Well, 5 is 5 to the 1. So you add 3 plus 1 to get x to the 5 to the fourth. And that comes out to 625. 3 to the second times 3 to the 0. Well, you add the powers. 3 to the 2 plus 0 is 3 squared is 9. 2 to the power 2 times 3. You multiply the powers. 2 to the power 2 times 3. 2 to the 6 is 64. Now, each of these is sort of a trick question. A number to the 0th power is 1. A number to a 0th power is 1. Here, ooh, trick question. Which do you do first, the 0th power or the negative? Well, okay, we'll get to order of operations later. But yes, in general, you do a power before we do a times a negative 1. So you get, this is a 1 times negative 1 is negative 1. If a to the 9th, a to the negative 2 over a is what? We'll write this a in the denominator is a to the first. You add these in up in the numerator, we add the exponents. A to the 9 plus negative 2 over a to the 1. Here we're dividing by a to the 1, so we subtract to 1. A to the 9 plus negative 2 minus 1 comes out to a to the 6th. If a squared a to the 4th cubed is what? Well, we add the exponents here, a to the power 2 plus 4. It's a to the 6th, all that cubed. Now, repeated exponents, means we multiply the exponents, a to the power 6 times 3. That's a to the 18th. This 2x squared times 5x to the 6th is what? Okay, first thing we do is we distribute the second power over these two terms, two factors. 2 squared x squared 5x to the 6th. And now we just scramble things around. 2 squared times 5, that's 4 times 5. X squared times x to the 6th, we add the exponents, x to the power 2 plus 6. 4 times 5 is 20, 2 plus 6 is 8. And you get 20x to the 8th. Now here's a complicated one. 5z to the negative second squared times z cubed is what? Well, first distribute the second power. 5 squared, z to the negative second squared, z cubed. All right, so we'll keep the 5 squared. Z to the negative 2 squared, you multiply it, you z to the negative 2 times 2. Keep the z cubed. 5 squared is 25, negative 2 times 2 is negative 4, z to the negative 4, z to the third. Add the exponents, 25 times z to the negative 4 plus 3. These add up to negative 1, 25z to the negative 1 will do. Or we can rewrite that as 25 over z. Now here we have 3, a to the 4th, b to the negative 2 cubed. That times a to the 2nd, b to the negative 1. What is that? Okay, first thing to do is distribute the third power over each of these factors. Here, 3 cubed, a to the 4th cubed, b to the negative 2nd cubed, a squared, b to the negative 1. Okay, in this step, 3 cubed is 27. A to the 4 cubed is a to the 4 times 3 is a to the 12th. B to the negative 2 cubed is b to the negative 2 times 3 is b to the negative 6th. A squared, b to the negative 1. So 27, a to the 12th, b to the negative 6, a to the 2nd, b to the negative 1. These two powers of a, you add the exponents, 12 plus 2. These powers of b, you add the exponents, negative 6 plus negative 1. Get it all together, you get 27. A to the power, 12 plus 2 is 14. B to the power, negative 6 plus negative 1 is negative 7. 27, a to the 14th, b to the negative 7. And last step, we write this negative power in the denominator as a b to the 7th. So you get 27, a to the 14th over b to the 7th. Okay, now, scientific notation. Let's get back to this. Here we go. Scientific notation. It's called that because in science, you get all these huge, ridiculously huge and ridiculously small numbers. And it's annoying to write all the zeros. because you know, if your hand gets tired, you miss a zero or you write it twice, and already you're off by a factor of 10, which means very wrong. So this is a way of writing it more compactly. You write a number in this form: n times 10 to the p. N is a number between 1 and 10. P is a whole number, the magnitude of the number. So 3.2 times 10 to the negative third, that's 1,000th times 3.2, so 0.0032. Here's 3.2 times 10 to the third, that's 1,000 times 3.2, it's 3,200. 137,000, you rewrite that as 1.37 times 10 to the fifth power. 0.00137, that's 1.37 times 10 to the negative third power. Now these orders of magnitude, these have names of their own, and I think it's worth noting. A number from 0 to 99 is in the tens, so it's 10 to the first is the order of magnitude. For 199, 999 is in the hundreds, 10 to the second power. From 1,000, 9,999 is in the power of 10 to the third. 1000 to 99999. This has, I think this deserves a name of its own, and it has a name of its own. It's some old-fashioned one, but I like it, namely myriad. So something in the order of 10 to the fourth, in hundreds of hundreds or tens of thousands, is known as a myriad. Something in the hundreds of thousands, 100,999,999,000, 10 to the fifth, that has a name. It's called a multitude. These are obsolete words, which I really think deserve to be revived. Okay, so here 1 million to 9.9999 million. Well, that's in the millions, 10 to the sixth. Going 3 powers of 9 to 3 powers of 10 up from there. Here we have 1 followed by 12 zeros, 9 followed by 12 nines. No, 9, 1 followed by 9 zeros, 9 followed by 9 nines. These are numbers in the billions, 10 to the times 10 to the 9. And I got to tell you, I remember when they started talking about trillions. Up till a certain point, all the numbers they talked about was billions. Now they're talking trillions. 1 followed by 12 zeros, 9 followed by 12 nines, that's 10 to the 12th power, or trillions. And of course, there's more to come: quadrillions, quintillions, sextillions, septillions, octillions, nonillions, decillions, never mind. So these are all orders of magnitude. Okay, the reason why we use scientific notation is because in science, you wind up some very large or some very small numbers. You want to be able to write them efficiently. So look at this horror. 0. bunch of zeros, 203. Well, it's 2.03. We write it, this part, I think it's called the mantissa, with the leading decimal in the ones, point the rest of it. Okay, now 10 to what power? Now you have to be careful. One way to do it is to start with this point, decimal point here, and move it to just the right of this leading digit, counting how many decimal points you have to follow. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have to move the decimal point 9 places and move it to the right because this is a tiny number. So therefore, we have a negative. So 10 to the negative 9. That times 2.03. Now here we're going to have a very big number, so we 10 to a positive thing. 5.016 goes here. We take this decimal point, move it to the left. 3, 6, 9, 12, 15, and one more makes 16. 10 to the 16. Sometimes you have a number that is not quite in proper scientific notation. 23.65 times 10 to the 6th. This is not from 1 to 10. So we have to rewrite it as such. 23.65 is 2.365 times 10 to the 1st. That times 10 to the 6th, you add the decimals, the powers, and you get 7. 2.365 times 10 to the 7. Or 0.0317 times 10 to the negative 2. Again, this is not between 1 and 10. We have to rewrite it as such. So move the decimal point 1, 2 to the right, so you get 3.17, and because this is a tiny number, it's times 10 to the negative 2. 3.17 times 10 to the negative 2 times 10 to the negative 2. Add these powers, negative 2 plus 10, negative 2 makes a negative 4. Get 3.17 times 10 to the negative 4. Scientific notation is good for noting large numbers and small numbers, but also for multiplying and dividing them, because powers of 10 are easy to multiply. Just add or subtract. So 1.3 times 10 to the 4th times 7.8 times 10 to the 5th. First, we multiply these two together, 1.3 times 7.8. Then 10 to the 4th times 10 to the 5th, you add the exponents, 4 plus 5. Now this comes out to 10.14 times 10 to the 9th. But whoops, this is not between 1 and 10, so we have to rewrite it. 10.14 is 1.014 times 10 to the 1st. And that times 10 to the 9th means you add the exponents. You get 1.014 times 10 to the power 10. That's the ratio. That's this product. Here, 2.686 times 10 to the 10th over 7.9 times 10 to the negative 7. So here we're dividing a big number by a tiny number, so it could be an even bigger number. But okay, first, 2.686 over 7.9 comes here. And here we have a ratio of powers of 10, so we subtract the powers, 10 minus negative 7. Now, if you work this out, this ratio comes out to 0.34. This comes out to 10 to the 17. Again, this is not quite in proper scientific notation, because this is not between 1 and 10. So we rewrite this as 3.4 times 10 to the negative 1. Then 10 to the negative 1 times 10 to the 17th, you add the exponents. And result, 3.4 times 10 to the 16th is this ratio. Let's do something, we'll go back down here. So, right in scientific notation, 693,000, big number. Well, okay. So the leading three terms are 693, so 6.93. Times 10 to what? Well, we start with this decimal point, move it over to the left. 1, 2, 3, 4, 5, 6, 7. So 6.93 times 10 to the 7. Now remember, this is a big number, so it's a positive 7. Here we have 72000. Oh my goodness. Well, leading two terms are 7, 7.2. We move the decimal point from here. 3, 6, 9, 12. Okay. 7.2 times 10 to the 12th. This is the number in the trillions. 0.000028536. Well, okay. Leading terms in this part, 2.8536. There you go. And move the decimal point to the right because it's a tiny number. 1, 2, 3, 4, 5. So 10 to the negative 5th. Here you have 0.001213. Again, I believe this part is called the mantissa, is 1.213. Move the decimal point 1, 2, 3, 4 to the right. So 10 to the negative 4th. Another way of looking at it for these small numbers, at least, is that you can count how many decimal points, how many places you have to move the decimal point to move it just to the right of the leading figure. Or equivalently, you just count these zeros. 1, 2, 3, 4, 10 to the negative 4th. 1, 2, 3, 4, 5, 10 to the negative 5th, and so on. Here we have a complicated ratio. 1.295643 times 10 to the 9th over 3.610 times 10 to the negative 17 times 2.511 times 10 to the 0. Oh, that's a 0, not a 6. My apologies. All right, fine. Now, here's a question. This has 4 significant figures. This has 4 significant figures. This has 7 significant figures. That's far too accurate for these two. Only 4 significant figures accurate for these two. So the 7 significant figures aren't useful. You can't really use them. So the thing as a result should be at the least accurate of all its inputs. So therefore only 4 significant figures, which is what we'll do. All right, now first, 1.295643 over 3.610 times 2.511. Okay, 10 to the 9th here. Now we're in the negative 17 is in the denominator, so we minus a negative 17. Oh, this is a 6, and we subtract the 6. Okay. Now, all right. This, we work it out. And again, there are only 4 significant figures that justified. So write it to 4 figures, it's 0.1429. 9 minus negative is 17, minus 6 comes out to 20. And again, this is not quite right form. You have to rewrite it as 1.429 times 10 to the negative 1. That times 10 to the 20th, negative 1 plus 20 makes it 19. So 1.429 times 10 to the 19th. Now here's a cool one, I think. Distance to the sky. Distance to Proxima Centauri. I mean, we talk about literally astronomical numbers. Well, here are some literally astronomical numbers. A light year is 5.9 trillion miles. Light travels 5.9 million miles in a year. Proxima Centauri that's the closest star, mind you, is 9.3 light years away. It takes light 9.3 years to get from Proxima to here. How many miles is that? Okay, we start with 4.3 light years as the distance, and we multiply by this. It is a unit conversion factor. 1 light year equals 5.9 times 10 to the 12th miles. So this ratio equals 1, so it's called a unit factor. It converts because if you multiply this times this, then light years will cancel, and we're left with the units of miles. So we take our 4.3 light years and multiply by 5.9 trillion miles per light year. Light year units cancel, we're left with 4.3 times 5.9 times 10 to the 12th miles. And after a little bit of work, where this turns out 4.3 times 5.9 is bigger than 10, so we move over a decimal, move a power of 10 over, and get 2.5 times 10 to the 13th miles, 25 million miles away for the closest star. It's a big universe. Okay, I think that covers that. Let's shut this down.